Hi, my name's Tim Cooper. I'm a Principal Applications Engineer for Semtech, and I'm going to be talking to you today about one of our projects from this year, which is a new version of Corecell designed to perform listen before talk and spectral scan. Today's workshop then is going to be guiding you through the process of setting up a single board computer as a LoRa gateway. Maybe you've already got an industrial SBC in your application, in which case you can turn it also into a LoRa gateway. Before we do this, we're going to talk a little bit about LoRa Corecell, what it is, what it can do, and some of the latest developments from this year. Next then, I'm going to go through the whole process of setting up your single board computer as a LoRa gateway. And then I'm going to go on to demonstrate some of the new capabilities of spectral scan and listen before talk of the Corecell reference design. Corecell is a reference design for SX1250 and SX1302. We have 4 different bill of materials then to address the 4 main global sub-GHz regions. We also have some new and improved radio functionality that I'll talk about as well and demonstrate today. And we also have then, of course, this PCIe format, which makes the device easy to use. And if you have a PCIe slot on your single board computer already, then the time to take a Corecell gateway to market should be about the duration of this workshop. Okay, so let's talk a little bit more about some of these improved functionalities. So we've already been through the effort of certifying Corecell for the world's major ISM bands. As a consequence then, when you go to the Semtech website, you can go and download the certification reports for that region. For each region then, we also have a full set of design collaterals, including the Altium design package as well, if you're using Altium Designer. Of course then as well, there's the bill of materials specific to that region. All of the performance reports as well, all of the characterization measurements that we've made, those are also all online. And in addition to that as well, there is an evaluation kit user guide that's actually common to all of the different versions of Corecell and show you how to set up your Corecell gateway, and from which a lot of this talk and this workshop has been inspired as well. So it's a good reference. So here we have the block schematic of Corecell for the 800 and 900 megahertz bands, so Europe, US and Japan. You can see that we have a single RFIO that we use. This then goes to a Skyworks front-end module that we use to output up to plus 27 dBm and to reduce our noise figure in receive mode. In the receive path, one new feature then is we actually split to 3 radios. So we split to the 2 SX1250s, and we have another path that's going to a dedicated SX1261. And the role of the SX1261 is to provide 2 new functionalities. Those are listen before talk and a spectral scan functionality that we'll come on to in a moment. In addition to that, one of the other new features we have is an MCU which acts as a USB device. This means that we can now connect directly to a USB host. Similarly then, for the China reference design, we don't need the front-end module, and so to reduce costs then, we simply have appropriate filtering and a low noise amplifier. We still have SX1261 to act as a dedicated LBT and spectral scan device, and we still have this USB interface as well. So here you can see then the 2 boards with what's on them. So on the left hand side we have our Chinese reference design, on the right hand side we have the rest of the world. They're all very common. The main difference is of course the front end module. One of the main improved functionalities in Corecell is this ability to use the onboard SX1261 to perform spectral scan. And this is one of the things that we'll go on then to demonstrate as well. But the idea is then that this allows you for a given gateway to see what kind of RF environment that gateway is operating in. And here we can see then we have a couple of examples on the right hand side of a quiet environment, and on the bottom right you can see here we have a signal present at 868 megahertz. So spectral scan is configured from within the global config JSON file. Here we have then a few settings that we have to determine. The first one being to enable the spectral scan. And spectral scan then operates in 200 kilohertz channels, and we simply specify a start frequency and the number of channels that we want to scan, and that will determine what bandwidth we'll scan over, and that will happen in 200 kilohertz steps. We then also can specify how many scans we want to do per channel. In case there's a bursty interferer, we might want to do multiple scans per channel to make sure that we pick that up. And so the last point here then is the pace, and that's simply the number of seconds we want to leave between full scans. Each scan point here, you can see, takes 8.2 microseconds, so the whole scanning process is pretty quick, but you'll see that in the demos in a minute. One of the other improved functionalities we have in this new version of Corecell is Listen Before Talk. Again, using the same SX1261 we're using for spectral scan. We have a list of downlink channels that are defined again in the config.json file, and if the gateway is asked, or Corecell is asked to transmit on one of those frequencies, then it will perform a Listen Before Talk before transmitting. So if you're not familiar with Listen Before Talk, here's what we mean. You can see here we have an uplink from a LoRa end device that is received by our Corecell gateway, and we know then we have these two receive windows that will open for downlink from the serving gateway. In this case, we have the new version of Corecell, so we perform our LBT before we're permitted to transmit on those channels. And you can see in this first instance here, the gateway encounters interference, and so the transmission is not permitted. When we get to the second window, another Listen Before Talk operation is performed, and if there's nothing present above a certain power threshold, then the gateway is allowed to downlink. Okay, here are the JSON configuration parameters we mentioned a minute ago for configuring the LBT functionality. So the first one obviously is just to simply enable LBT. The second one is the target RSSI. So here, if a power is detected above this power when we do our clear channel assessment, then we know that the channel is occupied. We also have then a list of channels, and for each of those channels we have several parameters. The first one is the center frequency of that channel. Next is the bandwidth of that channel. The third one is then the scan time. So there are two valid scan times. We can either scan for 128 microseconds or 500 microseconds, and that's the time we're actually listening for our LBT. And the last one then is the available TX time once we've performed that clear channel assessment. That's how long that window for transmitting is open for to the gateway in that channel. And the other improved functionality that we've alluded to, of course, then is this PCIe format with the USB host. And that means that we've paid attention to the consumption requirements, the mechanical requirements of the PCIe interface, and the USB interface to allow us then to plug straight into a PCIe interface. So the final points here then, before we start getting into the workshop itself, you can see that we have these transmit output powers as a function of which band we're operating in. An important improvement then in 13.02, of course, is that we have 16 LoRa modems. We have 8 dedicated over the full SF range, and we have another 8 to help with capacity in the range of SF5 to SF10. And then we have a couple of other dedicated modems here, one with the variable LoRa bandwidth, another one dedicated to FSK, and also, of course, we have our separate LBT and spectral scan SX1261 receiver, and all of those are configured as per normal in the global JSON config file. Okay, so on to setting up our industrial SBC as a gateway. So here then, instead of using this, which is the LoRa Corecell evaluation kit with the PCIe reference design and the Raspberry Pi, for industrial use we need something a bit more self-contained, so we're going to have this then instead. This is an Arbor Technology single board computer, and you can see down here that we actually have directly the PCIe slots on the board that we're going to use to make our gateway with. And so they end up with something a bit more self-contained and robust for industrial applications. So here we have our single board computer, and the first step then obviously is to get the box open. So on this one we have to start with the screws on the heatsink, and then take both the ends off. The reason we need to take both the ends off is that one of them has the RF connectors. We need to remove one of those. The other side then has a heatsink which connects to the case from the board, and you see here it's a bit fiddly to get off. And there it is, it's that bit underneath there we have to get out of the way. So now we can take our Corecell, carefully connect the UFL connector, they're ever so fragile, seat it in the PCIe slot, make sure it's well seated, and then screw it down. And that's really all there is to the installation then. So the next step, obviously, put the case back together, being careful with that heatsink again, and then yeah, it's just the reverse of the process for opening the case. And then once that's all done, the last step is the antenna. So we fit our Sub-GHz antenna, making sure it's on the right port, and that's our Corecell gateway ready to use. With the hardware setup complete, we can now turn our attention to the software setup of the SBC. So here's a quick list then of some of the prerequisites. So I'm going to start with a clean install of Lubuntu, and it's necessary to install all of these packages before we get started with the demos and the installation shown here. So let's get on with the software installation. The first step then is to clone from GitHub the HAL and packet forwarder for the Corecell. So here we go to LoRaNet SX1302 HAL.git, and we're going to clone that into our home directory. That will then go into a directory called SX1302 HAL. And the first thing we're going to do is just quickly compile that. And then while that's doing, there's a target.config that we need to modify because we're not installing on a Raspberry Pi. We just need to change the ID of the local host in there. So just look in the 1302 HAL directory and then target.config, and here we can see that the user is Pi, and we need to change that to Tim on this platform. There we go. Save that and close that down. The next step then is to just quickly create an SSH key so that we don't have to type our password in lots and lots of times when we do the final install of the software. So we make the key and then copy that ID over, and then we can get on with the installation. Let's put my password in. Okay. So now we need to perform a make install, and then we need to perform, once that's finished, make install conf. There we are, and that will make our global config files. There we go. The following step, once that's compiled, is to flash the STM32 MCU firmware. So here we need to put the MCU into boot mode. So there we go, shut the device, there we go. And now we're in boot mode. The next thing is to download the DFU util that we're going to use to flash the device. So there we go, we can do apt-get that. That then quickly downloads. So once that's downloaded, then we can go ahead and flash the MCU. And here then, for the path, once we're in MCU bin, just type RLZ and that will give you the release version of the firmware, and then we can flash that, see the progress bar advancing, and now that's programmed and ready to use. The final configuration step then really is simply just to check that everything's working. So we go back into our bin folder, and here we're going to use 2 programs there. We're just to quickly check that everything's working. So we're going to check the communication with SX1261 via our USB interface. Just tell you which device to use. There we go, and then once that's running, there we are. We should see communication between our host and the SX1260, and now we're going to do the same for the SX1250. Let it run again. There we are. So that means everything's compiled and we can talk to the hardware on the board. Now that our gateway is set up and installed, I'm going to go and demonstrate some of the new capabilities of LoRa Corecell, namely then spectral scan and listen before talk. So to do this, we're going to need to have a spectrum analyzer as well, so we can see what's happening in the spectrum around us, close to our single board computer, so we get a similar picture. And we're also going to have an SX1261 kit, and that we'll use as our interfering signal. We're going to begin by looking at the listen before talk functionality. So to do this, we must enable it, of course, in the JSON config file, which can be found here. Then you see there it says LBT enable must be set to true. So we save that, close that, and then we can open up the terminal. And then within the terminal then, we can start the packet forwarder, which would have operating in normal operation of the gateway, and telling it that we want it to use our USB config file for Europe. Okay, there we go. And the packet forwarder is now up and running. So also then within the packet forwarder installation, there's another set of utilities that we can use to, in this case, send packets. So this is called net downlink, util net downlink. And here you can see we're going to take our second example here, and we're going to use this then as inspiration for our tests. We're going to change a couple of things. So I want to do test at 868.1, and here then I'm also going to add a few more packets, and I'm going to add a jump, so we transmit on 2 frequencies, 200 kilohertz apart, and the explanation of all that's in the help description there. So wait for the packet forward to be ready, and then we're sending packets over the air, and that's what it looks like from the util net downlink side of things. So now then, if we run that again, but look this time at the output on the spectrum analyzer. So here I'm looking at those 2 frequencies, 868.1 and 868.3. And we'll be able to see here when the packets start transmitting. There we go. So because the analyzer is sweeping and the chirps from the LoRa is also sweeping and its packets going on and off, the picture slowly builds up over time on the blue trace, which is the max hold from the spectrum analyzer. And then we can see run it again. There we can see both of those channels being used, with the LBT being performed beforehand. Now we're going to run exactly the same command, except this time I'm going to set up an interferer on that second channel on the 868.3 megahertz. So here you can see then the packet's running. And here I'm going to use the SX1261 to then act as my interferer at 868.3 MHz. Here I'm sending GFSK preamble. There's the view on the spectrum analyzer, and we can see the blue max hold picture. We have that modulated signal that's always there, right on the second of my 2 LoRa downlink channels. And here we see that the Corecell is using the onboard SX1261 to perform listen before talk, and we're only seeing downlinks then, using the lower of the 2 frequencies where there is no blocking signal. So that's working LBT. Here we have a view of both the output of the util net downlink and the packet forwarder. And this is just to show you what the output looks like in the packet forwarder if the LBT criterion for preventing the gateway from transmitting is met. And so we're going to stop both of those, scroll back up and see we still have our interfering signal there, and you can see here the packet was not sent at 868.3, whereas here you can see that the packet was transmitted at 868.1. So we're getting information in the terminal then. The next demo then is the spectral scan, and here we're going to use another utility similar to the util net downlink. We have util spectral scan as well. Difference being in here we have both the application that will perform the spectral scan and some Python that will process the data. And so here we're going to run our spectral scan, and we're telling it here that we want to start at a certain frequency, remember, and run for a certain number of steps, each spaced at 200 kHz apart. So if we want to start at a frequency of 863 MHz, so the bottom edge of the European ISM band, then we need to do 31 steps to get to the top edge at 870 MHz. And so here as well, I'm just going to tell it what the name of the log file will be. There we go. And so those results will be written to a CSV file with that log file name. That's the actual output from the spectral scan, the same as would be written pretty much to the log file. And so now I can use the Python script just to visualize that output. Here we go, using that CSV file. And there we have it. So there we see our picture of the spectrum. We know we have our interferer at 868.3 MHz, which we can also see there. And then just for comparison, we can have a quick look on the spectrum analyzer, and we can see the same thing. So that wraps up today's workshop and presentation. Just a couple of last points here. This first link is where you'll find all of the design collaterals we discussed and the user guide that this workshop was based on. Next then is the link for the tools and software to download that we used in this workshop as well. And then lastly, you can see the 4 part numbers for the various evaluation kits for each of those regions. So thank you very much for your time and your attention. And yeah, thanks. Have a good conference.